Today we're going to be talking about ionic Lewis structures. To begin with, these things correlate very well with what we just discussed, that of our electron configurations. So remember, electron configuration's whole point is helping us figure out where those electrons exist. So now, today, we're going to be talking about forming those electron elements into ionic bonds. And ionic bonds are those bonds that consist of a stealing or a taking of electrons. And so we have to know where those electrons exist. Specifically, we really care about those valence electrons. So remember, those 1A, those elements in group 1A, how many electrons do they have in their outer shell? 1. And 2A, 2, 3A, 3, 4, 5, 6, 7, and 8. Okay, so remember, these were they end in your S1, your S2, your S2P1, your S2P6. These electrons are what enable us to figure out how stuff is going to be bonded together. In today's lecture, we're going to really talk about ionic compounds. Later on, we're going to talk about covalent. And so really, the electrons, where they exist in the valency of an atom, is going to tell us how atoms are going to combine together. Alright, so in this case, what do we know? What do we remember about them? Which atoms or elements are going to form positive charges? Which ones are going to form negative? How do you know this? And why? If you need to stop and go back and review this material, I do suggest you do that, because that is going to be vital. You need to be able to know without a doubt that, oh, elements in group 1A, what charge do they always form? +1. 2A, what do they form? +2. Get a periodic table. Write these things down. Okay? 3A, what do they form? +3. 4A, they're not really involved in, neither is 4 or 5A. They're not really involved in ionic bonding formation. And 6A, -2. 7A, -1. 8A, nope, they're content and happy. They're extremely stable. Okay, so you need to be able to just do that right now without really thinking about it, knowing that the reasoning behind it is because if you have one electron in the outer shell, it's a whole lot easier to lose that electron than it is to gain one. Okay, or to gain 7. Alright, so remember, what is an ionic compound? It's composed of a metal and a nonmetal. Why is that? Well, if these form positive charges over here and these form negative charges over here, in order to form a positive charge, you're giving up an electron. What are you giving it up to? One of these elements that need an electron in order to form a negative charge. So that's why you've got your metals on this side of the periodic table, and you have your nonmetals on this side of your periodic table. If you have a hard time remembering which is which, just find silver, find gold. Those are metals, so therefore you know the ones on the left-hand side have to be your metals, the ones on the right-hand side have to be your nonmetals. So why do they always compose of a metal and a nonmetal, or cation and an anion more specifically? Because opposites attract. You need your cations to give up electrons in order for your anions to form their charges. Alright, so these are the type 1 ions. A type 1 ion is basically everything we've been talking about so far. They are ions where there is only one possible charge for the cation. The transition metals, for instance, we haven't really talked about them. Why? Because they can form metals with various charges. You could have a +2 or a +3. Whereas lithium, guess what? Only forms +1. So type 1 ions are those that exist only having one possible charge. No more. Oops. Type 2 ions, therefore, have more than one possible charge. So mostly these are all going to be within your transition metals. And so you'll have a chart like this that you can use on the exam and that kind of thing, where you're able to see that you've got iron 2+, iron 3+, that kind of thing. Okay? Cobalt, it can form 2 charges, cobalt 2+, cobalt 3+. Notice the Roman numeral correlates with the charge. So whenever you're naming a type 2 ion, you can't just say like a lithium ion. It's got to be chromium 2, chromium 3. And the Roman numeral includes the charge of the cation. Notice also, type 2 ions, they're cations, and so they're always going to be these transition metals that produce more than one possible charge. This is not an exhaustive list. There is more to it, but this is kind of the main list that you'll be utilizing in this class. So, type 1 type 1 ions, those are going to be these three. Your 1A, your 2A, your 3A. Type 2, that's going to be your transition metals because they form more than one type of charge. Alright, so what we're trying to learn today is how are we going to combine them to form ions and form ionic compounds. In order to do that, we're going to do what's typically called cross the charge. Cross the charge is just simply the short way of simply saying make the charges balance out. Meaning, it's easy to see that if you have O2 minus combining with beryllium 2 plus, it's easy to see that one has a 2 plus, one has a 2 minus. So you can combine these two together in BeO because the charges balance out. But what if the charges don't balance out? Crossing the charge is simply the way of making them balance out. What I mean by that, first of all, we have to remember that we have to write our cation is always written first, and our anion is always written second. Additionally, the subscripts must be reduced. Meaning, if we had Be2, O2, you can divide both of those by 2, so you must, because you can, to make it be BeO. Okay, and that's kind of the general way we always write ionic compounds. So cation followed by anion, and then you want to write your subscripts, and they're reduced. So now when we cross the charge, if we use this BeO, the beryllium oxide as an example, crossing the charge means, and let me grab a different pen color, that we go bring this down here and this one down here to form Be2O2. And then it's simply a matter of reducing it to BeO. Alright, let's try another one. I never finished that BeO. Alright, let's try another one. What about sodium with sulfur? If we want to cross the charge, then your 2 must come down here, and your 1, because that's understood to be 1, right, must come down here, meaning Na2S1, cross the charge. Your 2 comes down, your 1 comes up. So that means, since you don't have to ever write it a 1 is understood, the NaS would be the ionic compound that's formed when you combine sodium and sulfur. Okay, let's do another example. What about aluminum with selenium? Cross that charge. Go ahead and give that a try on your own piece of paper. I hope you got two aluminums mixed with 3 seleniums, meaning you need 2 aluminums in order to balance out 3 seleniums, because that would give you a total of 6 positive charges balancing out with 6 negative charges. So 6 plus would be on this side and 6 minus would be on that side, so they're balanced out. So that's the same thing as cross the charges. Additionally, you can easily go in the reverse direction. So I'm going to go in reverse. What if I have gallium chloride? If I did not know the charge of each of these, I could figure it out by reverse crossing the charges. So let me switch my pen color one more time. So whatever that subscript is becomes a superscript and vice versa. So it would be gallium, the 3 comes up, and then chlorine, the 1 comes up. So that would mean gallium 3 plus, chlorine minus. So whenever I say cross the charges to figure it out, that's exactly what I mean. Because on this side, I basically have a 3 plus charge being balanced with 3 negative 1 charges, means 3 minus, and so it's balanced out. So whenever I say cross the charges, what I mean is do this exact thing where you combine the elements in such a way where the charge is balanced out. So take each superscript and turn it into the subscript for the other compound. Alright, you want to practice one more? Go ahead and do this one on your own. Mix calcium and fluorine. Mix, let's do sodium and oxygen. And then let's do magnesium and sulfur. So these are the neutral elements, but if they want to form ionic compounds, you got to turn them first into ions. So first off, figure out what charge each one of these atoms must have. And you can go ahead and pause it right now, do this on your own, and then check your work. That's what I would recommend. Cross your charges. And then make sure they are all reduced. Okay, and that's how you create an ionic compound, is you look at the element, figure out what charges should form, and then combine them. Alright, next we have these polyatomic ions. Basically, polyatomic ions are groups of elements that are covalently bound within them, but the whole group that is covalently bound together has a net charge on it. Meaning, this negative charge on acetate does not belong to any individual element. It belongs to the group. And because of that, the whole group can be treated just as an ion can be. And so you can cross the charges for polyatomic ions the exact same way you can cross them for ions. Let's give this a try. So meaning, what if I combined acetate with sodium? What charge does sodium have again? A plus. And so we want to write sodium first. And then the acetate is CH3COO or CO2. If it helps you to put in parentheses, please do. Now cross that charge. So the negative comes down, the positive comes down. You end up with NaCH3COO, or 2, excuse me. Okay. And let me see if I can erase that. Alright, let's try another one. What if we combine ammonium ion with oxygen? Oxygen forms an O2 minus. So we've got, I'm going to go ahead and draw a line. NH4, once again I recommend putting in parentheses, with O2 minus. Cross that charge. NH4. Now this is where I normally will see an error, is sometimes you'll just write it like right here. That doesn't make sense unless you put a parentheses around it. So that would be your final answer. NH4 in parentheses 2. That way the 2, you know, carries over to both of them. So in this example you'd have 2 nitrogens, 8 hydrogens, and 1 oxygen. Okay. Last one. Let's try phosphate with magnesium. So we've got magnesium with the 2 plus with our phosphate ion. Cross those charges. Ends up with magnesium, and there's 3 of them. And phosphates, there's 2 of them. So anytime you have polyatomic ions combining together with a cation or an anion, doesn't matter, either one, you combine them in the exact same way. The idea is you're still trying to get the charges to balance out. Alright, additionally now we can write Lewis structures of these ionic compounds. Now this, people sometimes get confused because they see Lewis structures and typically write Lewis structures for covalent compounds. We'll do those in our next lecture. But today we're going to look at how do we write the Lewis structures for those compounds that we just drew. Alright, so what's literally happening? So for instance, in the example I have drawn out here, calcium. If you look at calcium on the periodic table, it has 2 electrons, which is what you see each of these dots above calcium are. you have 2 electrons for the calcium. When it loses those 2 electrons, it becomes calcium 2+. And so we represent that by putting calcium in brackets and the charge outside. Chlorine's the opposite. It starts out with 7 electrons around it. It gains an electron. So now it went from having 7 electrons to having 8 electrons. We put that in brackets and we put the charge outside of it. Then, if you were to combine calcium and chlorine, it would form calcium chloride, which we see here, where there is 1 calcium and 2 chlorines. Then, in order to write the Lewis structure for just the ionic compound, you simply write it just as you see here, where you've got an understood 1 for calcium, but it is 2+. Then there are 2 chlorines, all of them are negative. And so that makes your 2+ balance out with 2- to have a charged balanced compound. The name of it now is calcium chloride. Well, how did I know that? Okay. Well, these are all, in this example, they are all type 1 ions. So in naming type 1 ions, what you have to do is you simply take the first name of the first element, so calcium, it stays the same, calcium. Then the second one was chlorine. So instead of saying calcium chlorine, what you do is you replace the ending with IDE, calcium chloride. So for instance, if we were to name sodium and mix with oxygen, what would it be? Sodium and then oxide. So remove the gen and replace it with IDE. Okay. Aluminum. Some of these are a little tricky. So aluminum and then sulfur, remove the gives us sulfide. What about this next one? This one's not tricky. So what do you think? What's its name? Sodium, remove the ending, chloride. Good. Okay, so let's give these all a try. So sodium, it starts out, write the element symbol, and we can actually do that for all of these. Okay, how many electrons does sodium originally start with? 1, so give it the 1. Aluminum, how many did aluminum start with? 3. Sodium started with 1. So because it started out with less than 4, they're all going to form positively charged ions. So sodium wants to lose its 1 electron, so it becomes a positive. Aluminum wants to lose all 3, so it becomes 3+. And then, I didn't really mean to give you the same 1 twice, but there you go. Okay, now oxygen starts out with O, with how many electrons around it? 6. Okay, sulfur, same thing, 6. Okay, and then chlorine starts out with 7. So oxygen starts out with 6, so it needs to gain 2 electrons in order to have 8 in the outer shell and become content. So that's why it forms 2 negative. Same thing for sulfur. And then chlorine wants to just gain 1 to be content. So that's why it becomes negative. Okay. Now cross the charge on those things. We have sodium with the plus and oxygen with the 2-. Cross that charge. Forms Na2O. Okay. Aluminum sulfide. What does it form? Al2S3. Sodium chloride. What does that form? NaCl. Okay. So then how do we write the Lewis structure for these compounds then, for this one, for this one, for this one? So sodium, how many are there? There are 2 of them. Then we write its Lewis structure. And then how many oxygens do we have? Just 1, so you don't have to write anything in front of it. And then write its Lewis structure. Okay, and then we do the same thing for aluminum. There's 2 aluminums. Its Lewis structure is Al3+. And notice all the cations should have no valence electrons shown for the ions, and all the anions should have 8 electrons shown in their valence. And then there are 3 sulfurs. So S, 1, 2, 3, 4, 5, 6, 7, 8. And that's how you write the Lewis structure for aluminum sulfide. Then sodium chloride. Draw it with all 8 electrons around it, and you're done. And there's only one of each. Okay, so that's how you write Lewis structures for ionic compounds. So since it's ionic, you need to show that the ions are being lost or gained, not shared. So when you have a structure that you're asked to draw and it's ionic, you're showing the individual electrons that exist around the element, meaning calcium, no electrons, but it has a 2+ charge, so you put that in brackets. Chlorine, it has 8 electrons because it stole one. That's why it has a -1 charge. Alright, so here's kind of a flow chart I hope that it helps you name these compounds. So type 1 is what we just discussed, where you write the name of the cation first, don't change it at all. Then you write the anion, but instead of having whatever ending it had originally, you replace it with IDE. And then your type 2, you do it the exact same way, but the only difference is this middle part. And in parentheses then, you put whatever the charge is. Okay, so if it's like cobalt 2+, you write cobalt, and then you put 2 in parentheses. And since it's always a cation that has these multiple charges, they're assumed to be positive. So you just simply give it a Roman numeral. So you've got your 1, your 2, your 3, your 4, your 5. Those are your most common. Okay. I'll go ahead and write that out. 1, 2, 3, 4, and 5. Okay. Then for covalent compounds, you write them the same way, except for you use these prefixes. With the one exception, you never write mono if it's the first prefix. Okay, no mono for that prefix. Mono does go for this prefix. Okay, so meaning, if you have carbon dioxide, that means you have carbon as the name of the first element with dioxide. So di, you look up at these prefixes over here, di means 2. So carbon dioxide, CO2. What about hydrogen dihydrogen monoxide? Dihydrogen, so there's 2 H's, monoxide, H2O. So anytime you saw those like horrible email spam letters going around talking about the dangers of dihydrogen monoxide and how it kills a lot of people, it's water. Okay, H2O. So that's how you name type 1 compounds, type 2 compounds, and covalent compounds. Additionally, if you have a polyatomic compound, you don't have to make any changes to them ever. Okay, so for instance, if it's an anion, you just write the name of the polyatomic next to it. So say it's sodium phosphate, that means it's just NaPO3. Okay, and if we go back, if we look at phosphate, it's PO4 3- charge. Oops. PO4 is what I meant, right? With the 3- charge. So we cross those charges. It would be Na3 PO4, and that would be sodium phosphate. Okay, so this IDE only works if it's not polyatomic. If it is polyatomic, you just keep the name phosphate. Now let's practice naming our compounds. So the first step is figuring out whether the compound is ionic or covalent. So let's look at our first one. We have sulfur and we have oxygen. Are they both nonmetals? Is one a nonmetal and one a metal? They're both nonmetals, so because of that, that means it has to be covalent. So they're both going to be found in the upper right-hand corner of the periodic table. They both would want to form a 2- charge, so there's no way they can form an ionic compound. So in naming them, there's one sulfur, so that'd be mono, but we don't include mono as a prefix if it's the first element, or if it's the first thing that's written. So no mono, and then there's 2 oxygens, so that makes di. So we have sulfur, dioxide, changing that root ending. Okay, so that's sulfur dioxide. The next one, xenon with fluorine, and there's 4 of them. So xenon, where is that on the periodic table? It's over here in group 8A. What do we know about group 8A? Very stable. They don't want to form ionic compounds. They can, in some cases, be forced to form covalent, which is what we've got right here. So covalent. So how do we do that? Once again, the first one stays the same. It's mono, so we don't write mono. And then 4. How do we say 4? Tetra. Xenon, tetra, fluoride. Okay, this next one. What do we have? Alright, so we've got a polyatomic ion. That's the thing we can tell first. If it's not binary, aka we have more than 2 elements, chances are it's going to be a polyatomic ion. So in this case, we've got a polyatomic ion, so that means we have an ionic compound. So let's reverse cross those charges and see what we get. Fe3 plus CO3 2 minus. Fe3 plus, type 1 or type 2 ion? Type 2. Then carbonate, CO3 2 minus. That's what we have on this one. CO3 2 minus. So how do we write that? Iron and then carbonate, just like that? No, I'm missing something. Roman numeral 3, iron 3, carbonate. Good. Now the next one, magnesium, and then sulfur, and then oxygen. Once again, polyatomic. So let's figure out what those charges are. Let's reverse cross them. So we've got magnesium plus, and then SO4 plus. Minus. Okay, so if SO4 is negative, magnesium is plus, they're going to be balanced. But what's the problem with that? There's a couple of problems, but the first one, magnesium. What charge does it have to have? 2 plus. So that means your magnesium should be plus 2, and that makes your sulfate be minus 2 in order to cross them out and make them balance. Is that true down here? Sulfate ion, SO4 2 minus? You got it. That's exactly right. So in naming this, it's magnesium. Do we have to put a Roman numeral? Nope. It's a type 1. And then sulfate. Good. Okay, now what about boron mixed with bromine? Okay, boron. It'd be right there, so it should form a 3 plus, right? And bromine's here. What happens if you've got boron 3 plus mixing with bromine minus? Cross those charges, we get BBr3. Is that what we have? No, so it cannot be ionic. It has to be covalent. So since it's covalent, we name it diboron tetrabromide. Good. Now we're going opposite. We've got the name, and we need to figure out the compound, the formula for it. So first of all, write down each of the elements. Lithium, what charge does it have? Positive. Fluorine, what charge? Negative. Because of that, because you know it did not have mono, di, tetra, any of that in the naming of it, you know it has to be our ionic. And so lithium fluoride, cross those charges, LiF. Now silicon dioxide, we have di in the word, so we know it has to be covalently bound together. So silicon, there's no prefix, so it must be mono. So silicon dioxides, there must be 2 of them. So SiO2 is the formula. Vanadium 3 sulfide. So because it's got a charge on it, it must be a type 2 ion, vanadium 3 plus, and then sulfide. What is sulfur's charge? 2 minus. So in order to cross those charges then, we get V2S3. Carbon tetrachloride. Carbon, we see the word tetra, so we know it has to be covalent. So chlorine with 4 on it. Carbon tetrachloride. Then lead 2 plus, so we know it has to be a type 2 ion, so it's an ionic compound. And then acetate. Let's go look back over here at acetate. There's our acetate ion. So CH3COO minus, cross those charges and we get Pb CH3COO, put a 2 outside there for the parentheses. So that makes lead 2 acetate. CH3COO. Did I miss an O? Nope. Okay, I got it. Good. Alright, and that's how you decide how you name stuff. So you first have to figure out, is it ionic or is it covalent? Then within that you have to figure out the specific rule to follow in naming. For instance, you know it's ionic if it's got a cation and an anion, or if it's got a polyatomic ion, or if it's nonmetals and metals. The charges on the ionic compound must balance out, and so that's where that crossing of the charges comes from. Then, before you naming it, make sure you decide if it's ionic or covalent, because that's where I see students going wrong, is they're trying to name ionic compounds with covalent rules, or vice versa. So make sure you decide if it's ionic or covalent first. Then, type 2 and type 1 ionic compounds are named the same way, but the one exception. Type 2 ions have to have the charge of the cation written in parentheses. That way you know what the charge is. Then when you name polyatomic ions, you keep the whole word. So instead of changing the ending to IDE, you keep the name as it stands. And then naming covalent compounds requires the use of prefixes. So your mono, your di, your tri, your tetra, that kind of thing. And so using all of this, you should be able to figure out what the formula of a basic ionic compound and a basic covalent compound is just by looking at the name, or vice versa. Figure out what the name of a compound is from looking at this formula. And so that's kind of the whole purpose of today's lesson. And if you've gotten that, good. If not, go back through and try and work through it one by one. You should be able to practice this lesson very easily just simply by looking at the periodic table and just mixing stuff together, and then practice your naming.